Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay, and I'm back with yet another geometry video for you all. And today's lesson topic is all about the Fermi process and density. But before we jump into today's topic, please make sure to smash that subscribe button down below, hit that like button on this video, and turn on post notifications, hitting that little bell icon right next to the subscribe button so you don't miss out on any of our channel's latest uploads here at eCoreAcademy. Feel free to also utilize the comment section down below and drop a comment. We'll always look at your comments, try and implement any feedback that you're trying to give us in any videos to come in the future. We really do appreciate it. As I was saying, our whole theme of today's lesson, our whole topic lesson, is all about the Fermi process. We're going to look at exactly what the Fermi process is, how we calculate it through different types of problems, and then we're going to apply it to density problems as well. So we're going to identify what the Fermi process is, what density is, and then we're going to correlate them together with multiple problems. This lesson is much more problem-based, and I actually wanted to shorten it a lot, so please be expecting a much shorter lesson, but try and absorb this information as it is much more complex as compared to the rest of the geometry topics that we've done. It's a lot different, more calculating with the numbers rather than concepts. Moving on to our first slide. This is our introduction to our Fermi problems. What exactly is the Fermi process? Now, I know you may have clicked on this video thinking, what exactly is this? I really need to get to know this. I probably should have already known this. Don't worry. This is something much more higher level math correlated. So it's used in higher level math, a lot of times in college math and AP calculus topics. So this has to do with an estimation process. I'll give you the exact definition. So the Fermi process is the process of estimation in which you will round your answer to the nearest power of 10 or the nearest power of 10 multiplied by a Fermi value. And the Fermi value is merely just your estimation to the nearest power of 10 or an integer multiplying that nearest power of 10. It's some sort of rounding method. And a Fermi value is merely an integer to express a specific amount of a given power of 10. So you can have 10 to the first, 10 to the 0th power, representing 1, 10 to the second, or even 10 to the third. And what you'll do is you'll multiply that integer value by that given power of 10 in order to round off your answer of a given value. So you're going to have to calculate your given values. Even through density problems, you're going to calculate your given values, and you're merely going to round it to the nearest power of 10 or the nearest integer multiplied by that power of 10. So you have to have good rounding skills as well. So this is another cool example here. This has to help with properties of what exactly we're doing. The Fermi process really helps us estimating values. Say, for example, if we needed to calculate the amount of cubic inches inside a swimming pool. Now, we know that cubic inches are extremely small, and we know that a swimming pool is extremely massive. Cubic inches are so small that they do not correlate properly with the swimming pool, but that's the whole challenge that we're faced with today. When we're given these improper measurements for such large volumes, we want to use the Fermi process to estimate. We can estimate that the pool has approximately 10 to the third cubic inches. That would be our estimation in the Fermi process. So we can estimate about 10 to the third cubic inches as our nearest estimation through the Fermi process. Because it's such a massive amount, we are just estimating off 1,000 cubic inches. It might be more, it might be less, even compared to the size of the pool. But we're going to utilize this vague information to develop a much vaguer answer, a general answer in terms of an exact power of 10. However, if we get much more specific and we're actually given the exact value, we can round that off by multiplying an integer value to that given power of 10. Moving on. Now we're going to introduce density. Well, let's look at exactly what density is and what are some of its properties. So this is our density problem overview. Density is the calculation of the compactness of a given object or area, and it specifically correlates with the unit of mass over the unit of volume given. This is a calculation that we come across oftentimes in science, especially in chemistry. So density has to do with the division or the calculation between the mass of a given object as well as the volume of that given object as well. So the mass is definitely your size. It can be pounds, weight, items as such, and then you're going to give it over a unit of volume that you're specifically given, and then over that given volume you can calculate density, which is the compactness of a given substance or a given item, which can even be people over a certain area, and then you can find out the density, how many people per that unit of volume. This is important to know when calculating population densities, as I was saying, and determining proper units of measure. So not just population densities, when it comes to absolutely anything, small objects to larger volumes or even correlated volumes. It's essential common knowledge in geometry. This helps you determine what proper units of measure you need to calculate in order to properly and accurately convey your message. In geometry, we're always calculating distance, area, volume, any sort of space taken up. So we need to be able to represent that in proper units of measure. It's always important to do so in order to be as exact and as precise as possible when giving instructions in the forms of reasoning. So let's look at another common example of density. I'm sure many of you think of density when you guys think of water and oil. So I oftentimes correlate that with the water and oil experiment. So what happens is water has a greater density than oil. Greater density than oil. Because of that, oil will float. So what this is saying is, per the amount of space that each item gives off, takes up, water necessarily has a larger mass per that given volume, and therefore it will stay on the top, and oil will automatically float on the top because it has, water will stay on the bottom, and oil will automatically stay on top. Therefore, they will never ever mix. Even when you put them and you try and stir them together, they will automatically separate from each other because of that differential in density. Only when mixtures have the same exact density do they start to mix entirely, and they stay in that same type of mixture in which they have an even amount of combination and culmination. So now let's take a look at the Fermi process on its own. So let's understand estimation with the Fermi process and how the whole process itself works. So the Fermi process is the estimation of given values using scientific notation. Scientific notation is something that you learned back in pre-algebra and your Algebra 1 days. Now this is just another easier process of estimation, but you're using the same process as scientific notation. But you're only rounding to the nearest values of to the nearest power of 10 or the dividend of that power. Now, it does get a lot more complex with the Fermi process because you will start to use fractions and other items as such to calculate much more accurate estimations. So you're limiting yourself to the nearest power of 10, but you're not limiting your Fermi value, which is your integer that you're multiplying to that power of 10, which makes it a lot more complicated. But we will get into that more in our extended problems video. Let's try and understand the basics with basic integers first. We will practice expressing values through Fermi and scientific notation. So I'm going to give you another random value here. So we have 684 as our value. So we're going to try and estimate this in our first level Fermi, which is going to be our general Fermi. So first level Fermi is merely just power of 10. So just the power of 10. And then second level is the integer multiplied by that power of 10. To estimate. We're not going to get into third level, which will be fractional form, trying to get the most accurate form. That's going to be in our extended problems video, so don't miss out on that. So let's take a look here at 684. Let's break this apart. We know that it's 600 here. We have 6 times 100. Let's do that. So we have 6 times 100, 8 times 10, and 4 times 1, all added together. So this is all added together. So what we're going to start off with, first level, we're merely just going to focus on 6 and 100. Same process as you would in scientific notation. 100 can be rewritten as 10 squared, and therefore it would be a 10 squared here. Most people stop here. Well, that's incorrect, though. So we see that we have 6 times 100. Now, what we're trying to do is, we're trying to see is 684 closer to 100 or closer to 1,000, the two nearest values of, the two nearest powers of 10. We know that 684 rounds to 1,000. Therefore, we're going to convey in terms of 1,000. So it's going to be 6 times 10 to the third. Closest power of 10. Sorry, not 6 times 10 to the third. It's just 10 to the third. I apologize. So we're just going to leave it at 10 to the third because we're just rounding it to only the power of 10. But for the second level, what we can do is we can round it to the nearest power of 10, the existent power of 10 that is multiplied by. In this case, it's being multiplied by 10 squared here. So we know that for the second level, we can multiply it 6 times 100, simplify 100 to 6 times 10 squared. And then that would merely be our Fermi second level value. And then afterwards, we can get even more specific by multiplying 6.84 times 10 squared. But I will get into that later, and we'll do like one problem with that in our extended problems video. So I'll just give you an example right here. If we're going to do third level, it would be 6 times 10, 6.84 times 10 squared. That's our third level of our Fermi process value. 6.84 times 10 squared. All right, moving on. Fermi practice part 1. Let's solve the following problem. I have a couple problems here that I really like to show you guys. So please stay in tune, stay in touch. So if you want to, you can pause this video before looking at this problem and before I go through it. Just try and solve it yourself, and then of course we'll reconvene and solve it through together. So the problem says a storage site has a total of 72 compartments, and when it comes to storing red and orange colored mulch, orange mulch piles have a volume of 30 cubic meters, whilst red mulch piles have a volume of 90 cubic meters. If they each share the same number of compartments, what is their combined value in terms of Fermi estimation and scientific notation? So we're gonna do first, second, and third level of Fermi, which is also conveying it through scientific notation. So that's our mulch. So we're given a storage site with 72 compartments, and so I'll put that down here. And they share the same number for the 30 cubic meters of orange and the 90 cubic meters of red. So let's start off with our orange cubic meters. Let's calculate how many piles are there of each. So yeah, let's calculate this. So we see that we have 72 total compartments, and we know that they're going to share the same amount each. So we're going to divide 72 by 2. We get 36 compartments. Then we're going to multiply our 36 by our given 30. 36 times 30. And this is exactly where I'm going to calculate this out for you right now, just because I want you guys to get used to it. But most people, what they do when they hear Fermi process values, you can merely estimate as given. So 36, that would be estimated to 3 times 10 to the first. And then afterwards, 30 would be 3 times 10 to the first as well. And then you'd merely multiply those values out to get 9 times 10 to the first. Sorry, no, 9 times 10 to the second. I apologize. Yeah. So you see that we get 36 times 30, so 30 times 30 is going to be 900. 6 times 30 is 180, so we get 1080 total cubic meters. What's my meters cubed? And then afterwards, we have our 90 cubic meters. Now, we know that we have 90 cubic meters piles for red, and they have the same amount of compartments, 36. So all we need to do is multiply 1080 times 3, because we have 3 times as much in each pile. So we're going to multiply 1080 times 3. We get 3,240 cubic meters. Then we're going to add these values together. So 3,240 plus 1,080 cubic meters. So we get 4,000, and we're going to 240 plus 80 equals 320. So it's 4,320 cubic meters. Now we're merely just going to estimate this in terms of our Fermi values. We know that it's going to be closest to our if we're going first level, then we know it's going to be closest to 1,000 rather than 10,000. So in first level terms, this can be estimated to 10 cubed. Second level, this would be calculated as 4 times 10 cubed. And then third level, this would be 4.32 times 10 cubed. And that is our calculation. Now let's move on to the next problem. All right, on to Fermi practice part 2. So let's solve the following problem here. Jed wants to know how many ping pong balls he can fit inside of his backyard pool. The ping pong balls have a volume of 3 total inches. Estimate the amount of ping pong balls that he can fit into the pool utilizing the Fermi process. So what we can do here is I want to round off these answers immediately. So we know that we have our given On to Fermi practice part 2. We're going to solve the following problem. Jed wants to know how many ping pong balls he can fit inside of his backyard pool. The ping pong balls have a volume of 3 inches. Estimate the amount of ping pong balls that he can fit into the pool utilizing the Fermi process. So what we're going to do here is we're going to estimate the volume of the given pool, and then we're going to be given the estimated volume of a ping pong ball, and then we're going to round that off to a closest power of 10. At the end. So we're going to calculate it and then do it at the end. So we have our swimming pool. We'll estimate our length to be about 10 to the first feet, our width to be 10 to the first feet, and our height to be about 10 to the first feet. And then that's going to be 10 times 10 times 10, which is 10 to the third. And then we know that 10 to the third is approximately 1,000. It is 1,000. We're going to multiply that by 12 to get the amount of inches. So we get 12,000 total inches. Now what we're going to do is we're going to divide 12,000 inches by our 3 inches. And then we're given a value of 4,000 inches. Now what we're going to do is we're going to estimate the amount of inches in our terms of our Fermi process. So first level would be 10 cubed. Second level would be 4 times 10 cubed. And our third level would merely be 4 times 10 cubed as well. All right, moving on to the next problem. Now it's density practice. I'm going to start to introduce density overall. So the equation that represents density is P equals M over V, and P is just our density. M equals mass, and V equals our volume. When it comes to multiplying or dividing amongst different rates of measure, you can merely cancel out the common factors or leave them as is. So let's multiply these values out. Let's do an example here. So let's say that we have 12 miles per second times 12 feet per mile. And this is just a standard equation. Not saying that there are 12 feet per mile, but this might merely be a 12 feet distance moved in every single mile. So this is just an example. So what we would do here is we'd cancel out our miles on both sides, and we would merely get 12 feet per second, as shown. Moving on to our final problem for density, part 2. So let's solve the following problem. Montana County has an area of 5,480 square miles and a population density of 6 people per square mile. What is the population? Give an estimate in Fermi estimation and then the exact answer. So let's start off by calculating this. We know that P equals M over V, but we can always change that equation around. In this instance, we're given what P is, so P equals 6, and then V equals 5,480 miles squared. P equals people, 6 people. So now what we're going to do is we're going to twist this equation around. We're trying to solve for in this case, the total population in this case. So that's the amount of people per place, so that's going to be our mass. So mass equals P over RV. So P times V. It's going to be P times RV. Right here, because if we multiply both sides by M, and then we are going to divide both sides by P to get M equals our population, or our population density multiplied by our total amount of miles here to get the total population for this given mass. So M equals P times V. So in this case, we're going to substitute that. So M equals 6 times 5,480. And in this case, we're going to merely start the Fermi process here in this density problem. So we're going to say that 6 is approximately 10 to the first. 5,480 is approximately, or 5 times 5 point. We'll do second level for now. So 5 times 10 to the third. M equals 10 to the first times 5 times 10 to the third. So that's going to be M equals 5 times 10 to the fourth, approximately. That's our approximated value in this case. But we do know that it is fairly close. That's about 50,000 people here. But the exact value is approximately a little bit over 30,000. It's in between 30,000 and 50,000 as our estimation. Alright everyone, so that'll be it for today's video. Please make sure to like and subscribe down below. Hit that like button on this video, and please make sure to turn on post notifications so you don't miss out on any of our channel's latest uploads. Check out our website at www.ecoreacademy.org to get full unlocked access to what we as an online e-learning platform actually offer to you, with integrated note sheets, quizzes, and worksheets that go along with each and every single one of our video lessons. Also, feel free to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. And please visit our socials down in the description box below at Facebook, Twitter, and Instagram. See what kind of interesting content we have out there, and use those mediums to share all of our videos. Once again, everyone, I hope you guys enjoyed this video. This has been AJ, and I will see you guys in the next one. Peace.